do now is discuss some of the single and double slit experiments. But first we need to start with a few definitions and diffraction. Diffraction is just the spreading out of waves. So if I have parallel wave fronts coming in and they hit this barrier, and then there's this slit of some diameter d, the waves are going to curve out like this. All right? So all diffraction is the spreading of wave around an edge or a barrier. Now, let's talk about what monochromatic means. Mono means single. Chromatic means color. So it's just one color, one wavelength, one frequency. Now, we can find monochromatic light from polychromatic light or white light if we shine white light. This is white light. White light, of course, presence of all the wavelengths through a prism. And then, because of their wavelengths, remember from light, they will refract at different angles. And so you can get this rainbow effect. All right. Now, let's talk polychromatic light. It's, of course, more than one wavelength. Now, all the wavelengths together is white. Well, this, of course, is our monochromatic on the other side of our prism. So poly, more than. It doesn't have to be all of them, but it just has to be more than one wavelength. Now, Huygen's principle is fascinating. He says that every point on a wavefront acts as a new source of disturbance. So, if I have waves coming in, I've got the characteristics spreading out. Each one of these is a source of a new wave. Huygen's principle can explain both reflection and refraction. So this, my light is coming in and it's reflecting. Remember, it's reflecting off the same angle. Reflecting is to bounce. Reflect. This is mirrors. This is our geometric optics. Or refract. Refract means to bend. And this is, of course, lenses. Now, you can see dark fringes. Just take two of your fingers or your three fingers, your index, middle, and thumb, and hold them very, very close together. Make a very small circle and hold it up to the light. You're going to see dark fringes. And this is an example of what we're talking about. Now let's talk about the science behind what we did. Suppose I have some light source, and the light source is, of course, sending light out in all directions. And we're going to follow one photon. The photon comes through, and it's got two slits it can go through. It is going to go through and follow this pattern right here without fail of light and dark. We're going to call them fringes. So this is a double slit. So we see what happens when we have a double slit. The light comes in, and you get this pattern of light, or where there's constructive interference, and dark. Light, dark. Light, dark. And it's paralleled on the other side. Let's look at the formula. The formula says if I have two slits that are separated by a distance d, and those slits are a distance L from a screen, this is your screen here, then light of some wavelength coming in, hitting these slits of distance d, is going to follow the following formula. L times the wavelength has to equal y, or the distance, all right, to the first, or to the bright slit, to the bright, well, this is actually the center of the bright band, the bright fringe, times the distance between them. So L is the distance between the slit and the screen. Lambda is the wavelength of light coming in. And if you'll notice, these two are the ones that are horizontal. This is equal to D, the distance between the slits, times Y, the distance between the center maximum and the bright band. Now, characteristics of double slit. You need to know this. We will go through the FET simulation, or this is not if that simulation actually is it. We'll go through this simulation in class. But there's a bright central band. As the wavelength increases, the pattern spreads out. We'll bring this up, as the distance to the screen increases, the pattern spreads out. As the distance between the slit decreases, the pattern spreads out. Let's see what this means. Y is the distance between the patterns. This is L lambda over D. Let's see. As the wavelength increases, that's going to increase the distance between the center and the bright band. As L increases, I'll do this one in blue. As L increases, this is also going to increase the distance from the bright central to the central to the from the bright central to the bright fringe. And then, of course, as the distance decreases, all right, that will also increase the distance between the center and the bright band. Now, single slit characteristics, they also have a bright central band. And basically, this is what happens if you don't have two, but you only have one. A narrower slit produces a wider central band, while a larger wavelength gives a wider pattern. We will analyze these a bit more in class with the single slit diffraction Java that we have here. Let's talk about diffraction gratings. Now, single slits and double slits are fine, but what happens if you have a whole bunch of slits? All right, so a diffraction grating, we have these in class, I'll show them to you, have a bunch of slits, all right, and they're uniform, unlike this, and they're very good at separating light into its spectral colors. The same is true with an oil film. You know how you see these cool colors on oil films and soap bubbles? What causes that? Well, this diffraction is what causes it. It's a result of interference. Excuse me, not diffraction. It's a result of interference. Say I have an incident light wave. It comes in, part of it's reflected and part of it's refracted. As it is refracted and then reflected again, it comes out in phase or out of phase. And depending upon how it comes out of the oil film or the soap bubble, depending upon the thickness of the oil film or the soap bubble, you get different colors. So clearly, you can see this soap bubble has different thicknesses because it's showing different colors. Now, we're not going to get into this, but this is just a diagram of what a light ray does. The incident ray comes in, it gets refracted, and then it refracts again, and we get all of the different colors. Just remember, the next time you see a beautiful soap bubble, we're talking about constructive and destructive interference. We're talking physics.